Something extraordinary is happening right now on the most distant planet in our solar system, and the scientists watching it are genuinely baffled. Neptune, the ice giant sitting nearly 4.5 billion kilometers from the Sun, has been doing things that contradict everything the models predicted. Storms that should be growing are shrinking. Temperatures that should be rising are dropping, and then reversing, and then doing something else entirely that nobody has a clean explanation for. We have only visited Neptune up close once in all of human history. A single flyby, a few hours of close observation 35 years ago, and even from that brief encounter, the planet left us with more questions than answers. Now, in 2026, with the most powerful space telescope ever built, turning its infrared eyes toward the outer solar system, Neptune is revealing details we have never seen before. Ring structures so crisp and clear they look like something from a science fiction film. Atmospheric circulation patterns that span the entire planet. 7 moons visible simultaneously in a single image. And beneath all of that visual spectacle, a set of physical mysteries that the best planetary scientists on Earth cannot yet fully explain. Stay until the end. Because what has been discovered recently about this blue giant is going to make you look at the edge of our solar system very differently. Let us start with the basics, because Neptune is genuinely one of the strangest objects in our cosmic neighborhood, and understanding why requires a sense of the scale involved. Neptune is the 8th and most distant planet in the solar system. It sits at an average distance of nearly 4.5 billion kilometers from the Sun. Light, traveling at 300,000 kilometers per second, takes more than 4 hours to cover that distance. When you look at Neptune through a telescope, you are seeing the planet as it was 4 hours ago. A year on Neptune lasts 165 Earth years. If you had been born when Neptune was discovered, in 1846, the planet would not have completed even a single orbit by now in 2026. We are exactly 1 Neptunian year past its discovery. The first and only time in human history this has happened. Neptune was the first planet predicted mathematically before it was ever seen. In the early 19th century, astronomers noticed that Uranus was misbehaving, its orbital position deviating slightly but measurably from calculated values. 2 scientists working independently, John Couch-Adams in England and Urbain Le Verrier in France, both concluded that an unseen gravitational body must be responsible. Le Verrier sent his calculations to the Berlin Observatory. On September 23, 1846, astronomer Johann Gottfried Galle pointed his telescope precisely where the mathematics said to look. And there it was, a small, luminous point that was unmistakably a planet, predicted by equations before a single human eye had ever seen it. For more than a century after that discovery, Neptune remained a distant mystery. The telescopes of the 19th and early 20th centuries showed little more than a featureless blue-gray disk. That changed in the summer of 1989 when the Voyager 2 spacecraft made its final planetary stop on a grand tour of the outer solar system. The flyby lasted only a few hours at close range, but those hours transformed everything we thought we knew about Neptune. Voyager 2 revealed a world of deep, vivid blue, streaked with enormous storm systems and white methane clouds. Most dramatically, it discovered the Great Dark Spot, a cyclonic storm roughly the size of Earth, rotating within Neptune's atmosphere. Winds measured at up to 2,100 kilometers per hour, the fastest ever recorded in the solar system. A planet receiving only 1,000th of the sunlight that reaches Earth, somehow generating the most violent weather of any planet we know. And then Voyager 2 left. And for 35 years, Neptune has had no visitor. Everything we have learned since then has come from telescopes, Earth-based observatories, the Hubble Space Telescope. And now, the instrument that is changing everything all over again. The James Webb Space Telescope has turned its infrared eyes toward Neptune, and what it has captured is the clearest, most detailed view of the planet and its ring system in 3 decades. The images are stunning, not because they show Neptune in vivid color, they do not. Webb observes in the near-infrared spectrum, so Neptune appears in gray tones rather than the iconic blue it shows in visible light images, but because of the structural detail they reveal. The rings of Neptune appear with a clarity never seen before. Not just the major rings, but the faint, diffuse bands that were barely detectable even in Voyager 2's images. The ring system suddenly looks substantial, defined, and remarkably structured. The Adams ring and the Le Verrier ring, named for the 2 scientists who predicted Neptune's existence, are clearly visible. And within the Adams ring, the mysterious arc structures, clumped concentrations of material that appear as bright nodes rather than a uniform distribution, are visible with unprecedented clarity. 7 of Neptune's 16 known moons appear in the Webb images simultaneously. Triton, the largest moon, glows brightly in the upper portion of the frame, and a thin bright band circling Neptune's equatorial region reveals something scientists are calling a global atmospheric circulation system, a structure that influences how the entire atmosphere moves, captured in a single image for the first time with this level of definition. But the visual revelations from Webb are only the beginning of what is currently baffling the scientific community. Because Neptune's atmosphere is doing something deeply strange. Here's the puzzle. Neptune is currently in its southern hemisphere summer. Summer on a planet where each season lasts approximately 40 Earth years because the full orbital period is 165 years. During a southern summer on Neptune, the southern hemisphere should be receiving slightly more solar radiation. Temperatures in the upper atmosphere should be rising, or at minimum, remaining stable. Instead, between 2003 and 2018, a comprehensive study compiling 17 years of Neptune temperature observations found that the planet's global average atmospheric temperature dropped by approximately 8 degrees Celsius. 8 degrees across an entire planetary atmosphere is an enormous shift. The measurements came from powerful ground-based observatories, including the Very Large Telescope in Chile, using instruments capable of analyzing a celestial body's temperature through its infrared emission signatures. The Spitzer Space Telescope contributed additional data points. The dataset was the most thorough temperature analysis ever conducted on Neptune without a spacecraft in orbit around it, and the result made no sense. The planet was cooling during its summer. The hypotheses being investigated include changes in the photochemical concentration of hydrocarbons in Neptune's atmosphere. When these compounds shift, they alter how much energy the atmosphere radiates in the infrared spectrum, which changes the temperature measurements. Similar processes have been observed on Saturn, where chemical interactions within atmospheric cloud layers have been shown to influence those layers' temperatures. On Neptune, the chemical processes appear to be intense enough to affect the temperature of the entire planetary atmosphere simultaneously. Another hypothesis involves Neptune's storm dynamics. The Great Dark Spot, Neptune's most famous storm structure from 1989, had already disappeared by 1994 when Hubble observed the planet again. A new storm had formed in a different location. Neptune's storms appear and disappear on timescales of years, and the formation and dissipation of these massive cyclonic systems may drive intense chemical reactions in the atmosphere that alter its energy balance. The storms might be cooling the planet even during summer by agitating photochemical processes that increase atmospheric radiation. A third hypothesis involves the sun's activity cycle. The sun goes through roughly 11-year cycles of higher and lower activity. Changes in solar radiation output, even relatively small ones, might trigger photochemical changes in Neptune's already chemically complex atmosphere, which could drive temperature variations in ways that current models do not yet adequately capture. But here is where the mystery doubles. Since 2018, the cooling has reversed. Neptune's temperature has been rising again, and it has risen rapidly, an average of approximately 11 degrees Celsius over just a few years. So the planet cooled by 8 degrees over 15 years. And then warmed by 11 degrees in far less time than that. A temperature roller coaster on the most distant planet in the solar system, occurring during its southern summer, defying every prediction the models made, and producing swings in both directions that nobody has a clean physical explanation for. Neptune is genuinely bewildering, and this is why planetary scientists are paying more attention to it now than at almost any point in the past 3 decades. The structure of Neptune itself adds layers to the mystery. Neptune belongs to a class called ice giants, alongside its neighbor Uranus. This distinguishes both of them from Jupiter and Saturn, which are gas giants composed primarily of hydrogen and helium. Neptune contains much higher proportions of heavier elements, particularly water, ammonia, and methane, in a state that sits somewhere between liquid and gas under the extreme pressures of the planetary interior. These exotic states of matter do not exist anywhere we can directly observe on Earth. Scientists suspect that somewhere deep in Neptune's interior, a form of water called superionic ice may exist. In this state, hydrogen ions move freely through a lattice of oxygen atoms, creating a material that behaves simultaneously like a solid and an electrical conductor. This exotic layer may be the key to understanding one of Neptune's other major mysteries. Neptune's magnetic field is powerful but profoundly strange. It is tilted approximately 47 degrees relative to the planet's rotational axis, far more than the tilts seen in any other planet's magnetic field, and it is not centered on the planet's core. It is offset, asymmetric, producing a magnetic environment that looks chaotic compared to the relatively organized magnetic fields of Earth, Jupiter, or Saturn. The suspected explanation is that the superionic water layer deep in the interior acts as an electrical conductor, and the geometry of that conducting layer, rather than the core itself, is what generates the magnetic field. But this remains a hypothesis. Neptune's interior has never been directly sampled or observed. Everything about what lies beneath the cloud tops is inferred from external measurements and theoretical models. Then there is Triton, Neptune's largest moon, which may be the most interesting single object in the outer solar system. Triton is massive enough to account for more than 99% of all the mass orbiting Neptune. It is larger than Pluto, and it orbits in the wrong direction. Every other large moon in the solar system orbits its planet in the same direction the planet rotates. Triton orbits Neptune in the opposite direction, a retrograde orbit that is physically impossible to explain as the result of Triton forming alongside Neptune from the same material cloud. The only explanation is capture. Triton was once an independent Kuiper Belt object, similar to Pluto, that wandered too close to Neptune and was gravitationally captured. The capture process would have been violent and chaotic, explaining why Triton's orbit is retrograde, slightly elliptical, and inclined relative to Neptune's equatorial plane. But Triton is also internally active. When Voyager 2 flew past in 1989, it observed geysers of frozen nitrogen erupting from Triton's surface and rising several kilometers into its thin atmosphere. Cryovolcanism. Active geology occurring at a surface temperature of approximately minus 235 degrees Celsius, one of the coldest surfaces in the solar system. The energy source for this activity is debated. Tidal flexing from the elliptical orbit is one candidate. Radioactive decay in the interior is another. And there is a hypothesis, not fully supported but scientifically serious, that Triton harbors a subsurface liquid water ocean beneath its frozen crust, kept liquid by tidal heating and perhaps radioactive warming, similar to what is believed to exist under Europa's ice shell or Enceladus' surface. If Triton has a liquid water ocean with chemical energy sources at the interface between the ocean and the rocky interior, the implications for astrobiology are significant. Life as we understand it emerged in liquid water environments on Earth. The question of whether similar chemistry could produce similar results in a subsurface ocean on a moon of Neptune, far beyond the traditional habitable zone, is one that cannot be answered without a spacecraft returning to this system. Which brings us to what comes next. Several missions to the Neptune system have been in various stages of proposal and study. The Trident mission concept, proposed under NASA's Discovery program, would conduct a close flyby of Triton at approximately 1,000 kilometers altitude, closer than Voyager 2 managed, with modern high-resolution cameras, magnetometers, and plasma instruments. The primary goal would be determining whether Triton has a subsurface ocean. A flyby mission of this kind would take approximately 13 years of transit time, meaning a launch in the late 2020s would produce Triton data in the early 2040s. The Neptune Odyssey concept is far more ambitious. An orbital mission that would spend years circling Neptune, studying the atmosphere, the ring system, the magnetic field, and the moons in sustained detail rather than a brief flyby. Odyssey would include an atmospheric probe that would descend into Neptune's cloud layers, returning direct measurements of temperature, pressure, composition, and chemical processes from inside the atmosphere for the first time. This mission would answer questions that no Earth-based or flyby observation ever could. And then there is the Triton Hopper, a concept that genuinely sounds like science fiction. A mobile lander that would travel across Triton's surface not by rolling or driving, but by jumping. The hopper would harvest nitrogen ice from Triton's surface, heat it to generate a propulsive gas jet, and use that jet to launch itself from location to location across the moon's surface. Multiple jumps, multiple landing sites, multiple surface environments, sampled across a single mission. The technology is in very early development stages, but has been studied under NASA's Innovative Advanced Concepts program as a technically feasible concept for this specific application. In the meantime, the James Webb Space Telescope continues delivering data. Its infrared observations of Neptune are providing information about the planet's atmospheric chemistry, temperature distribution, and ring structure at resolutions that were simply not achievable with any previous instrument. Every new observation adds detail to a picture that has been frustratingly incomplete for 3.5 decades. And the timing of all this renewed scientific attention is significant. We are at a moment when thousands of exoplanets have been discovered, many of them in the size and mass range between Earth and Neptune. These sub-Neptune and Neptune mass worlds appear to be extraordinarily common in the galaxy. They may be the most common type of planet in the universe. Understanding Neptune, the only example of this class of world we can study up close, is therefore not purely a question about our own solar system. It is a question about how common this type of planet operates across the galaxy, what their interiors are made of, how their magnetic fields are generated, whether they can sustain the conditions for liquid water at moon surfaces, and what their atmospheric dynamics tell us about planetary evolution in general. Neptune is not just a distant blue dot at the edge of our solar system. It is the key to understanding an entire category of world that may be the universe's most common form of planet. And right now, in July 2026, that world is doing something that no model predicted, swinging through temperature extremes during its summer that contradict the established understanding of how ice giant atmospheres behave, revealing ring structures through Webb's infrared eyes that are more detailed than anything previously captured, and harboring a captured moon that may contain liquid water and has geysers erupting from a surface that is almost unimaginably cold. The scientists watching are genuinely baffled, not in a vague or performative sense, in the specific technical sense that the data is inconsistent with the leading models, and nobody has yet produced a full physical explanation for what the instruments are measuring. That is the honest state of Neptune science right now. And if the history of planetary exploration tells us anything, it is that the planets that confuse us most completely are the ones that reveal the most important things about how the universe works when we finally visit them properly. Neptune has been waiting for that visit for 35 years. Everything it has shown us in the meantime suggests the wait will be worth it.